Hello everyone, welcome back to the MP Coding Linux Device Driver Development video series. In the last video, we discussed GPIO interrupt handling. Today, we are going to look at high-resolution timers. Before we dive into the code for our high-resolution timer, we first need to understand why the Linux kernel provides two different timing systems. In Linux, not all timers are created equal. First, we have normal timers, often called low-resolution timers. These timers are tied to the system tick, which we usually refer to as jiffies. In the last video, we used this type of timer for GPIO debounce handling. If I check how my kernel is configured, you can see that the Hertz value is set to 250. That means 1 second is divided by 250, which gives us a base jiffies resolution of 4 milliseconds. So in my case, the timer resolution is limited to 4 milliseconds. These normal timers use a data structure called the timer wheel. They are extremely efficient for handling thousands of simple timeouts, such as waiting for a network packet, where perfect timing accuracy is not critical. Next, we have hrtimers, or high-resolution timers. These timers do not wait for the system tick. Instead, they provide nanosecond-level precision by programming the hardware to generate an interrupt at the exact moment required. Internally, hrtimers are organized using a red-black tree, which keeps them sorted by their expiration time. You typically use high-resolution timers when every microsecond matters, such as in digital signal processing or real-time tasks. So the trade-off is simple. Normal timers save CPU power by grouping timer events together, while high-resolution timers give you very precise timing at the cost of more frequent hardware interrupts. Now that you understand the difference between these two timer mechanisms, let's get started with the implementation. Okay, I have created a new folder for the hrtimer example, and inside that folder I created a source file and a make file. Currently, the source file contains an empty init function and an exit function. Okay, let's start. To use the kernel high-resolution timer API, we first need to include the linux/hrtimer.h header file. Now, inside the init function, let's look at how to initialize a high-resolution timer. For that, we use the function hrtimer_init. This function takes 3 parameters. The first parameter is a pointer to the hrtimer structure. The second parameter specifies which clock source to use. And the third parameter specifies the hrtimer mode. So first, let's create a global hrtimer structure. Static struct hrtimer, and I will name it my_hrtimer. Now, in the hrtimer_init call, I pass the reference to my_hrtimer. For the clock source, I will use clock_monotonic. You can see that there are several other clocks available here. These are IDs for different system clocks, and you can choose one based on your requirement. In this example, I am using the monotonic clock. For the third parameter, I will use hrtimer_mode_rel. If we look at the definition of the hrtimer_mode enum, you can see that there are different types of hrtimer modes. You can read the definitions in the source code or search online. Here, I am using hrtimer_mode_rel, which means the timer expiration time is relative to the current time. Next, we need to set the callback function for the high-resolution timer. For that, we assign a function pointer to my_hrtimer.function. If we look at the hrtimer structure definition, we can see that this callback function must return enum hrtimer_restart, and it must accept a pointer to a struct hrtimer as its argument. Now, let's implement this callback function. I just copy this definition and paste it here in the source file. This function should be static. And I will name it hrtimer_callback. Here I will name this as timer. Inside this function, for now, I will return hrtimer_no_restart. If we check the definition of hrtimer_no_restart, we can see that there are 2 possible return values. One is no restart, and the other is restart. No restart means this is a one-shot timer. Restart means the timer is periodic. First, I will demonstrate a one-shot timer, and later I will show how to convert this into a periodic timer. Now, back in the init function, I assign this callback to the hrtimer structure. Next, I want to capture the current time when the timer starts. For that, I use the ktime_get_ns function, which returns the current time in nanoseconds. To store this value, I create a new global variable called start_time with type U64. U64 means unsigned long data type. Now, we need to start the high-resolution timer. To do that, we use the hrtimer_start function. This function takes the hrtimer structure pointer, the expiration time, and again the timer mode. So first, we need to define the expiration time of type ktime_t. I declare a static global variable of type ktime_t, and I name it period. Now let's update the hrtimer_start function. First parameter is reference to my_hrtimer. Next one is the period, and final one is the mode, which is hrtimer_mode_rel. Finally, inside the init function, I print a simple message to indicate that the timer has started. Let's go back to the callback function. Inside the callback function, I again read the current time using ktime_get_ns. Then, I print the difference between the current time and the start time, so we can see how much time has actually elapsed. Finally, in the exit function, we need to cancel the high-resolution timer. For that, we use the hrtimer_cancel function and pass the reference to my_timer. After that, I print a simple message to indicate that the module has been unloaded. There is one important thing we missed here. So far, we did not set any value for the timer period. Before starting the high-resolution timer, we need to initialize the period variable. For that, we use the function ktime_set. If we open the definition of ktime_set, you can see that it accepts two parameters. The first parameter specifies the number of seconds. The second parameter specifies the number of nanoseconds. So using this function, we can easily define our timer expiration time. In this example, I want to create a 1-second timer, so I set the period to 1 second. This means 1 second and 0 nanoseconds. Before load the module, let me initialize the module init function and exit function. Okay, let's build the file. The build was successful, so now let's load the kernel module. Before loading the module, I will open the dmesg buffer in another terminal, so we can clearly see the kernel messages. Sudo insmod my_hrtimer.ko. As soon as the module is loaded, you can see the log message printed from the init function, indicating that the high-resolution timer has started. After 1 second, the timer expires, and the callback function is executed. In the dmesg output, you can see the printed message showing the time difference between the start time and the current time in nanoseconds. If you look closely, this value is very close to 1 second. That is because we captured the start time before starting the high-resolution timer, so a few nanoseconds are consumed by the setup and scheduling process itself. Even with that overhead, the result is still very close to 1 second, which shows how accurate the high-resolution timer is. Next, I will show how to measure the accuracy between 2 consecutive callback executions using a periodic high-resolution timer. That way, we can evaluate the timing accuracy even more precisely. Okay, let's unload the module. Module unloaded. Now let's look at the periodic high-resolution timer. To make the timer periodic, the first change we need is in the callback function. Instead of returning hrtimer_start, we must return hrtimer_restart. This tells the kernel that the timer should be restarted after it expires. But returning restart alone is not enough. We also need to move the timer forward to the next expiration time. For that, we use the function hrtimer_forward_now. This function takes two parameters. The first parameter is a pointer to the hrtimer structure. The second parameter is the period by which the timer should be advanced. Now, with the current print statement, we cannot accurately calculate the elapsed time between two callback executions. Instead, I will store the timestamp of each callback execution and calculate the time difference later. For that, I define a simple array to store the timestamps. I set the maximum number of samples to 20. Then I declare a timestamp array and an index variable. Now I will remove these print lines. Now, here, I store the current time in nanoseconds using ktime_get_ns and save it into the array. I also increment the index, but only until we reach the maximum sample size. In the init function, everything remains same. Now let's move to the exit function. After clear the timer, I iterate through the collected timestamps. For each sample, I calculate the difference between two consecutive timestamps and print the delta value in nanoseconds. This allows us to see the actual elapsed time between two consecutive callback executions. Okay, that's all for the code. Now let's build the module. Now let's load the module. The module is loaded successfully. I will let it run for a few seconds so it can collect the timestamp samples. Now let's unload the module to see the results. As soon as the module is unloaded, the exit function is executed. In the dmesg output, you can see the printed delta values, which show the time difference between two consecutive callback executions. This allows us to clearly observe how accurate the periodic high-resolution timer is. You can see how close these time differences are to 1 second. Now let's quickly try a 1 millisecond timer. 1 millisecond means 1 million nanoseconds. So I will update the period value accordingly. Instead of 1 second, I now set the period to 1 millisecond. After updating the period value, let's build the module again. The build was successful. Now load the module, and then unload it to see the result. Here you can see the results. The time difference between consecutive callbacks is very close to 1 millisecond. This shows how accurate the high-resolution timer is, even for very small time intervals. So this is how we can achieve high-resolution timing in the Linux kernel using hrtimers. In the next video, we will start section 4, I2C and SPI driver examples, so stay tuned. If you found this video helpful, please like the video, subscribe to the channel, and hit the bell icon to get notified about upcoming videos. Thanks for watching, and I'll see you in the next one.